Imagine a nuclear power plant you can fit entirely on a high school football field. A reactor that can safely power a massive AI data center, physically cannot melt down, and arrives on the back of a truck. But before you plug it in, there is a multi-billion-dollar catch. To understand the catch, we have to look at traditional nuclear power. Building a conventional reactor is a massive, bespoke construction project. Every site is unique, requiring decades of specialized labor and custom engineering, which consistently pushes these mega-projects billions of dollars over budget. Yet our electrical grids are desperate for exactly the kind of constant, carbon-free baseload power that nuclear provides to replace highly polluting coal and gas plants. Enter the Small Modular Reactor, or SMR. This is a new class of advanced nuclear technology officially backed by the International Atomic Energy Agency, which is the UN's global nuclear energy watchdog. The core theory behind an SMR is strictly limiting its electrical output to 300 megawatts or less per module. A megawatt is a unit of power equal to 1 million watts, and 300 of them is enough to run about 200,000 homes. By keeping the module small, engineers can build the entire reactor on a standardized factory assembly line. Instead of constructing the reactor on site over 10 years, identical prefabricated modules are manufactured in a central facility and then loaded onto standard multi-wheel transport trucks to be delivered and plugged in wherever they are needed. SMRs treat power plants as mass-produced hardware rather than unique civil engineering projects. This approach attempts to bypass the high costs and unpredictable timelines that crippled the traditional nuclear industry. To make these compact, shippable reactors viable, engineers had to solve the most critical risk in nuclear energy. They call the solution passive safety. Let's look at a design from the American company NuScale. Their 77-megawatt module sits submerged at the bottom of a 10 million-gallon underground pool of water. Instead of mechanical pumps, heat naturally drives water up and around the steam generators, using pure thermal convection. If the facility loses power, the reactor shuts down. The pool safely absorbs the decay heat for days without any human intervention or backup generators. This design eliminates the fatal flaw of legacy reactors, which required massive electrical pumps to force cooling water through the core to prevent a meltdown. NuScale used this physics breakthrough to blaze a trail through the regulatory system. In 2022, they became the first SMR design to receive full certification from the U.S. Nuclear Regulatory Commission, the agency responsible for civilian nuclear safety. With approval secured, NuScale partnered with a group of utilities to build their flagship deployment, the Carbon-Free Power Project at the Idaho National Laboratory. This bar chart tracks estimated capital costs for the Idaho project. In 2020, the projected cost to build the plant was $3.6 billion. By 2023, inflation, bottlenecks, and rising interest rates drove that estimate up to $9.3 billion. The participating utilities simply could not absorb that kind of price increase. In November 2023, lacking enough financial subscriptions to continue, NuScale and its partners abruptly canceled the entire project. It was a harsh reality check for the entire sector. Mastering the physics of passive safety and clearing the toughest regulatory hurdles means absolutely nothing if the harsh financial math of the real world kills the project before a single shovel hits the dirt. If you're finding this deep dive into the complex economics of our future energy grid valuable, take a second to hit the like button and subscribe to the channel. NuScale's public economic stumble sent shockwaves through the industry. With over 80 different SMR concepts currently in development globally, the remaining competitors realized they had to urgently rethink their business models to survive. The industry fractured into two distinct strategies. The first is the legacy adaptation, led by GE Hitachi and their BWRX-300 reactor. Instead of inventing an entirely new reactor from scratch, GE took their already proven advanced boiling water reactor technology and simply shrunk it down. By using existing licensed components, they significantly reduced their engineering risk, which has quickly earned them massive financial backing and contracts in Canada and Poland. The second strategy goes in the complete opposite direction. Companies like the American startup Last Energy are acting as micro-disruptors. scaling their reactors all the way down to a tiny 20-megawatt output. Last Energy operates with a completely rogue business model for the nuclear sector. They refuse all government financing, and they design their plants using standard, off-the-shelf supply chains, borrowed directly from the oil and gas industry. By removing custom engineering and avoiding the red tape of government subsidies, they are promising a blistering 24-month delivery timeline. Their target customers aren't massive public utilities. They are private, power-hungry industrial manufacturers and the endless, energy-intensive server racks of modern data centers. Winning this market depends on logistics. Companies are now optimizing supply chains and standardized parts to bypass the construction bottlenecks that stalled previous generations of nuclear power. Right now, SMRs are moving from theory to active deployment agreements across the globe. Nations from Romania to Ghana are signing contracts to build these modular plants over the next decade. But the core economic paradox exposed by NuScale remains true for every single competitor. Shrinking a reactor doesn't automatically make it cheaper right out of the gate. SMRs only achieve their promised affordability through economies of scale. You have to build dozens of them to make the manufacturing process cheap enough to matter, and that requires massive, sustained upfront capital to survive the initial rollout. The ultimate winner in this sector will be the company that can secure enough funding to survive this financial valley of death, successfully transitioning from building bespoke prototypes to stamping out identical commercial units. The viability of carbon-free nuclear power now depends on the efficiency of the factory floor. To meet global energy demands, the industry must demonstrate it can manufacture reactors as reliably as it designs them.